Hello everyone and welcome to my video on rational indices. My name is Darren from Maths Guru. You're saying where? I'm saying Maths Guru, my little corner of the interweb where there's these videos, downloadable lesson notes and such more. Hopefully here to teach you rational indices. What are rational indices? Well, the learning objectives behind me are hopefully everything we are going to do today. Understand what it means to be a rational index, know how to manipulate rational indices, and know how to apply the learnings to a range of complex problems. Ooh, complex problems. And they do get a little bit complex, but more sort of tricky. I think it's more about practice and knowing what you can and can't do. Now, this is really a recap of the type of stuff we've done before. You've probably met rational indices in year 10. That's basically, no, I'm not going to spoil the excitement, yes, it just gets a little bit more tricky with methods. And if you're saying what is methods, it doesn't really matter if you're not from Australia. Rational indices are from universal mathematics. Now, if you can do me a massive favor and subscribe to my YouTube channel, that would be immense. It just lets me know that someone out there is watching and I'm not talking to myself. Now, a rational number, as it says here, is one which can be expressed as a fraction, or to borrow a definition from somewhere else, a rational number is one that is expressed as a ratio, i.e. a fraction, of two integers, where the denominator should not be equal to 0. For obvious reasons. If you try and divide by 0, you're going to get infinity. And that's a construct. It's not a real number. And anyway. So let's look at a couple of examples. Here we go. The square root of x. All right. So the square root of x can be expressed as x to the power of half. Now, why on earth would we ever want to express it as having a power of a rational number, x to a rational number? Hold the phone. Cube root of x to the third, quartic root of x to the quarter. And so hopefully pretty quickly you should notice that whatever, this number is in front is basically the fractional part of the power. Realistically speaking, we should write a 2 there. We don't though. I suppose through convention, we just know that if there's not a number there, it is a number 2. Now again, why is this important to us? Well, we've met lots and lots of index laws before. And just to recap one now, if I had x to the power of a times x to the power of b, we know that basically x to the power of a plus b, right? So when the base numbers or letters are the same and you're multiplying them, we simply add the powers. And there are a number of index rules out there that you should by now be really, really familiar with. One of the ones that I really enjoy, he says, no. One of the things I like is the idea that fractional indices can be expressed in different ways. Now, not so much with 1 over 2 or a third or a quarter, but if I have a to the power of 2/3, that is exactly the same as writing a to the power of a third squared, or a squared to the power of a third. Now, you're going to say, huh? Where did that come from? Well, you already know this rule because we knew that something like a to the b to the power of c was the same as a to the power of bc. When we have powers of powers, what do? We simply multiply them together. All right, so x squared all cubed became x to the power of 6, for example. All we're doing here is saying that's 2 lots of 1/3. 2/3, remember, is the same as 2 times 1/3. Which means we can therefore split it up into either 2 times 1/3 or 2 times 1/3. And you may turn around and go, well, what's the difference? Well, the difference comes when we work out whether this number here can actually be cube rooted. Because if it can, it makes sense to cube root inside the brackets and then square the number outside of squaring it and then cube rooting it when it might not have a natural cube root after being squared. Does that make sense? Sort of. We're going to do some examples now. Now, it's not going to be a very long video, but hopefully this will give you an indication of sort of how to do this. So let's have a look at part A. What do we got here? We got minus 64 to the power of a third. Now, I can't split this up because it's 1/3. It doesn't make any sense to do it otherwise. And so I've got to go back and say, well, that's now the same as the cube root of minus 64. Now, again, we can have cube roots of negative numbers. And so what we're looking at here is saying which number, when multiplied by itself 3 times, gives me minus 64. Well, in which case, hopefully, that's going to give me -4. Now, of course, you could put this into your calculator, but I would imagine these type of questions would be on a non-calculator paper. -4 times -4 is -16. 16. Times that by -4 gives me -64. We're done. What about B? And again, the trick to these questions is practice, practice, and practice again. 9 to the power of -1/2. Again, there's no fractional with 2/3 or 3/5 or 9/8 or whatever. So, well, the first thing I will remember is that Mrs. Hurst, love of my life, a bit creepy when you're 13, but moving on. That minus sign means that basically we reciprocate the fraction and we write it as 1 on 9 to the power of 1/2. Okay, well, power of 1/2 I know is the square root, so that's the same as 1 on the square root of 9. And we know that the square root of 9 is 3, and there we go, we get 1/3. What about part C? 16 to the power of, what is that, 5 on 2. Now, this is the example that I'm sort of saying. Now, because it's not 1 on something, it's 5 on, we can actually split that up. And there are two ways. We can either have 16 to the power of 1/2, 5, or 16 to the power of 5, then to the half. Now, I don't know about you, but one of these becomes so much easier to work out, because now that I know that we got a half, that is the square root of 16. Can I work out the square root of 16 before I then raise that to power of 5? Or am I going to try and work out what 16 times 16 times 16 times 16 times 16 is before square rooting it? Don't know about you, I am having a feeling that that would just be lunacy. And so that's 4 to the power of 5, which is 4 times 4 times 4 times 4 times 4. And yes, I am putting that into my calculator now to give me 1024. I cheated, I'm sorry. But in a pencil and paper example, you could probably do that. What's the next one? 64 to the -2/3. 64 to the -2/3. Well, that negative sign, thank you, Mrs. Hurst, gave me 64 to the 2/3. And that's 1 on 64. Now, I could do 64 squared to the power of 1/3, but that seems silly. So I'm going to do 64 to the 3rd and then squared, because that is the cube root of 64. What number, when multiplied by itself 3 times, gives me 64? 4. Did we already say it was 4? It was going to be 4. So that's the same as 1 on 4 squared, or 1 on 16. So there we go. That's the general basics of sort of 4 questions that sort of unpack the general stuff that you should be able to do. And then we get to example 2, which turns life a little bit more interesting, because the numbers here, I think, make the question way harder than something like this. And yes, you will have met something like this in year 10 or, you know, somewhere else if you've been doing maths outside of school. So let's have a look at part A first. Right, so part A gives me 3 to the power of 1/4, and we've got to simplify this. Now, to be able to simplify it, they're really looking for 1 power on the top and 1 power on the bottom. By that I mean 1 base to a power on the top and 1 base to the power on the top to the bottom, because at the moment we've got all sorts of bases. You know, this one here is 3 to the power of 1/4, that's 6 to the power of 1/2, that's 2 to the power of 1/4, and 16 to the power of 3/4. So they're all sorts of different bases. Wouldn't it be nice if we could split them up into just having sort of a 3 on the top to some power and a 2 to some power on the bottom? Spoiler alert, that's where we're going. So what we're going to do now is say that's 3 to the power of 1/4, and that's 6 to the power of 1/2, and that's 2 to the power of 1/4, divided by now 16 to the 3/4. That's 16 to the 1/4 and cubed. Now 16 to the 1/4 is 2, so that becomes 2 cubed. Okay, so now we've got a situation where we got 3 different bases. We've got a 3, a 6, and a 2. Wouldn't it be great if we could somehow get those into just 2? Well, hold on. Using the rule backwards, I know that 6 to the power of 1/2 is the same as 3 to the power of 1/2 times 2 to the power of 1/2. If you don't know why, it's the same idea that if I had the root of AB, that's the same as the root of A times the root of B, which is the same as A to the 1/2 times B to the 1/2. Okay, so again, we can use algebra to help us work this out. So what do we got here? So that's going to be equal to, so we've got now 3 to the power of 1/4 times 3 to the power of 1/2 times 2 to the power of 1/2 times 2 to the power of a quarter, all divided by 2 to the power of 3. Now again, I think a trick here is a lot of people would have written that as 8 and then probably would have got stuck from there. What I'm going to do is rub this out. So if you're going to download these notes from Maths Guru, my apologies. Maybe if you can download them and scribble this all over, that would make life a little bit easier. Right, so what have we got now? Well, we know that where we have the base numbers that are the same, we can basically now add the powers. Base numbers are the same, add the powers. So that's going to give me 3 to the power of a quarter plus a half is 3/4 times 2 to the power of 3/4 divided by 2 to the power of 3. Okay, so moving on to the next step. Well, we now realize that we can actually move this down here, and that's going to give me 3 to the 3/4 divided by 2 to the power of 3. We're going to turn that into quarters, which is going to be 12/4 times 2 to the minus 3/4, which therefore gives me 3 to the power of 3/4 divided by 2 to the power of 12/4 minus 3/4 is 9/4. Ka-ching, and there we go, it's simplified. Now again, putting numbers into this seems to make it way more complicated. I actually love the idea of my fractions because I can do the fractions much quicker than I can do here. So hopefully I've got enough space. What have I got here? So x, well, the first thing I notice is that I've got a power of a power. So that half multiplies by that -2 to give me x to the power of -1 times by y to the power of a half. We're going to times that as well by, well, again, powers of powers, x to the power of a 4 divided by y to the power of -12. Y to the power of -12. Well, y to the power of -12 basically just becomes y. So I can basically move this up here, and that x can move below. So I'm going to end up with y to the power of a half times y to the power of 12 divided by, or times by x to the power of 4 divided by x. That x can cancel with one of those to give me x cubed. And x to the power of a half times that is going to give me 25/2. So y to the power of 25/2 times by x cubed, I'm fairly sure, is the right answer for that question there. All right, and again, much simpler with the idea of letters than the numbers. But anyway, learning objectives are revisited. Do we understand what it means to be a rational index? We do indeed. It just means it's a fractional index. Know how to manipulate rational indices. There were a number of examples I've gone through. Know how to apply the learnings to a range of complex problems. One of those was certainly very interesting, and it looked at the idea that the square root of 6 is the same as the square root of 3 times 2, which was 3 to the power of a half and 2 to the power of a half. This is probably one for your summary book to make sure that you can put it in there just to nudge your memory and like, aha, I can do that way too. All right, well, I'm done. Thank you very much for watching the video. Hopefully it has been helpful. I'll see you again, hopefully in the next video. If you can subscribe, that would be awesome. Spread the word to your friends and teachers if you have found this video useful, or leave a comment below if you're on YouTube, and hopefully I'll see you in another video. Until then, take care.